Now let's suppose that we have the so I have my source charge. Now, if you remember, we said that gravity, so an electric field simply tells me a region of space where there is a force, just like the force of gravity. So whenever you have a positive charge, we said that the electric field lines always come out like this in all directions. And what I'm going to do is that I'm going to say that let this charge, so let the source charge has a value plus 3 microcoulombs. Then, so what I'm going to do is that I'm going to draw a circle. So let's draw a circle of these. So this is not really a circle, but this is more like a sphere, right? Because I cannot draw a sphere in just on a plane, but think about when you have a positive charge, right? The lines are coming out, so the field lines are coming in all directions. It's coming to the right, it's going up, left. So it's like a sphere, right? But I'm just drawing it like that. I hope you understand. So I'm going to say that this point, so let's say that this point is point A right there. This is point B, this is point C, point B. F, G, point E, point H. So we're looking at a sphere that has a radius of 1.0 centimeters. So what I'm saying is that the distance from here to here so because this is a sphere, the distance to point A is the same as the distance to point B, which is the same as the distance to point C, and so on. All the distances are the same, right? Now, what I want to do is that I want to calculate the electric field vector at each of those points. So what is the electric field at point A? What is the electric field at point B, at point C, and so on? So this is point B. Now I'm going to write this down, but you guys can check this calculation. So electric field at point A. So for example, this would just be KE Q divided by distance squared. And this will be pointing in the i-hand direction. So if you do this calculation correctly, you should get something like 2.7. 0 times 10 to the power of 8. All of that should be pointing in the i-hand direction. Now, let's take this angle here, 45 degrees. So all those angles are the same. So 45, 45, 45, 45 degrees. So all those angles are the same. Now, my question that I want to ask you is, what do you think the electric field vector at point B is going to be? in terms of magnitude, is it going to change?
No.
No, because distance is the same, charge is the same. So what changes here?
The direction.
It's just the direction, right? So if you solve this problem, you get exactly the same magnitude. So we can write this as 2.7. And now the direction is cosine of 45. I cosine 45. Now, if you understand what the electric field means, so so those lines that you see right there, those are lines of force. So, for example, if I put a test charge at point Q naught, it moves in that direction, right? If I put it at point B here, it moves like that. So wherever you put the test charge, the line of force tells me where that charge is going to move. Does that make sense? Now let's calculate the electric field at point C. What's the difference? So
Direction.
magnitude remains the same. What is the direction in this case?
In the J.
It's in the J direction. So this is just going to be 2.7 times 10 to the power 8 Newton per coulomb. J direction. And you can go ahead and continue to do pretty much the same thing. So I'll just add one more example here. For example, if you calculate the electric field at point H, which is this point here, you get the same magnitude, so 2.7 times 10 to the power 8 Newton per coulomb. But this will be, so as this is pointing like that, it means that the x component is negative, the y component is negative. So this would be negative cosine of 45.
The x is positive.
X is positive, right? I'm sorry. So plus cosine of 45 I minus sine 45 G, something like that. Yeah. So this line tells me, so if I put a charge here, Q naught, it moves in that direction. So these are lines of force. So lines of force and the direction. So the direction is the direction of motion. So if you have a test charge Q naught, it moves in exactly the same direction. Now, let's do one more example here. Now, what if I draw a second circle like this? But now let's take the radius of that circle to be 2.0 centimeters. And if I were to go back and repeat the same calculations, what do you think is one quantity that I need to change? It's just the magnitude, and by how? By what quantity? By what amount? 1/4, right? So if I double the distance, magnitude of the force is going to reduce by 4, right? So again, this brings us to that. If you remember, we said that the strength goes as 1 over distance squared. So if you just double the distance, the force is going to reduce, right? If I triple the distance, the force reduced by 1 over 9. Now, you could also see that by looking at, now let me show you something here. Now look at this point here, this point, and this point, and then look at this point and this point. You see that the distance between the lines are getting wider as you go out. And that's what tells you that the force is reducing. So as you go closer to the charge, the field lines are kind of like converging. So you have more force. As you go away from that charge, there is more separation between the field lines, it tells you that the field line is becoming weaker and weaker and weaker. All right, so that's something that, so I hope that at this point I've given you like a really solid understanding of what the electric field is. So let's go back to the PowerPoint. Any questions about this? Before I change my screen here, so let me share my screen.